So energy is often involved in chemical and physical changes. Water evaporating, chemical change or physical change? Physical change. There is energy involved in water evaporating. Right? Is it hot outside? Yeah. Does it make you sweat? Oh yeah. We're just all sweaty messes, right? When you get a breeze though, how does it feel? Feels nice, feels cool, right? That's because the evaporation of the sweat is removing energy from your body. So that state change, that physical change, is involving energy. Natural gas burning, physical or chemical change? Chemical change. If you see the word combustion or burning or exploding, those are big clues, chemical change. Is there energy associated with natural gas burning? Oh yeah. Why do we have a natural gas stove in the kitchen, and why do you light the burner? Because you want to put something on top of it and make it hot, right? It releases a lot of energy. So there's energy involved in these changes. This chemical change, releasing energy, it's a little bit harder to understand than a weight falling off the top of a building. So we put this 10 kilogram weight up here, and it has high potential energy. It's unstable, because you give it a little nudge and it's going to fall, right? We all know that. Babies experiment with this endlessly in their high chairs, right? They're always just knocking things off. Cats do that too, right? Cats just knock everything off because it's fun. It's like, oh, look, that happened. Oh, look, it happened again. They're just investigating. They're doing science. You give that a nudge, it falls. It had high potential energy. And as it falls, it goes faster and faster and faster, right? The kinetic energy increases. I don't know about you, but I would not want to be under that 10 kilogram weight, right? It's got a lot of energy, and it's going to damage whatever it hits, right? Down here, when it hits the pavement, it may or may not crack the pavement. Down here, it has low potential energy because it's more stable. It could probably just sit there for years. It's not going to fall off the sidewalk, right? It's stable. What happened to the energy that it had? It got dissipated as heat. Now that's something we might not notice. So it was high potential energy. As it was falling, its kinetic energy was increasing. The potential energy is turning into kinetic energy. And then when it hits the sidewalk, that energy has to go somewhere, and it gets transformed into heat. Things that smash into each other with a lot of energy get hot. Is that heat a useful form of energy? It depends. I mean, you could potentially, shouldn't use that word, you could possibly harness it somehow, but that's going to be difficult, right? And so this heat that gets released is probably not going to be very useful, but the amount of energy is conserved. When you burn natural gas, it has a high potential chemical energy. It's unstable. And in the course of the reaction, it goes to a lower potential chemical energy, and heat is released. That heat is a little more useful. It's easier to make useful. So systems with high potential energy have a tendency to change in a way that lowers their potential energy. Things fall down. They don't fall up. Things with high potential energy are less stable. They are unstable relative to things that are lower. Some chemical things, substances, have relatively high potential energy. Energy is concentrated in them. Trinitrotoluene, also known as TNT, because that word's like a tongue twister. TNT tend to undergo rapid chemical changes. You light a stick of TNT, can't even say that, kaboom, right? It is explosive. Where did the energy come from? It was stored within the molecules. And the process of that chemical change releases that energy. So We have terms for these types of reactions because many reactions give off energy and others absorb them. So if we have an exothermic reaction, again, these are prefixes. Prefixes exo and endo. Exo makes me think of exit. You go out the exit, right? So in an exothermic reaction, the reactants have higher potential energy and the products have lower potential energy. The difference in the energy of the reactants and products is the energy that gets released. So natural gas burning releases energy into the kitchen. It makes it hot, which, on a day like this, you maybe want to just eat a cold sandwich instead. But the reactants had high energy, the products had low energy. That energy was released. It went out from the chemical system. It's exothermic. Thermic refers to heat. So exothermic, heat going out. Endo means going in, into, endo. So here, endothermic, heat is going into, energy is going into. If your reactants have low energy, you can put energy into them, that the reactants can absorb energy and make products that have a higher energy. That can also happen. That's an endothermic reaction. The energy has to come from somewhere. Any questions? So identify each of the following changes as exothermic or endothermic. Water freezing into ice. Most students will say endo. That's not right. How do you, it actually gives off energy to freeze, which is not at all obvious. How do you freeze water? Well, you stick it in the freezer, duh. What is the freezer doing? Do you ever think about that? It's sucking heat energy out of the inside of the box and putting it outside into your kitchen. It's a heat exchanger. Yeah, it's a heat pump. It's sucking energy out of the freezer. Water freezing into ice is an exothermic process. I live in Reedley, which is surrounded by fruit trees, right? And in the winter, we sometimes get a freeze, which sounds really nice on a day like this. But they don't like it when the oranges freeze, right? Because it wrecks the crop, and then lots of people are out of work, and it just trickles and it messes everything up. How do you keep the oranges from freezing? What they do is they flood the fields. As the temperature of the air goes down and the water begins to freeze, it releases energy and keeps the air around it at the same temperature. And so it actually protects the citrus trees from freezing. It's exothermic. Now, how would you go about answering that on a test? Because this is a question that could show up on a test. You should be able to identify state changes as exothermic or endothermic. Well, this one is hard to think about. Think about the opposite. Ice melting. How do you get ice to melt? You put heat into it, right? So if ice melting is endothermic, then water freezing has to be the opposite, exothermic. Okay? How about natural gas burning? See, now you're overthinking it. Natural gas burning. Heat comes out, exothermic. Yeah, see, I tricked you on the first one. And you're like, okay, it's opposite of what I think. Just for that one. So you burn natural gas, and heat comes off, right? So heat coming off or something getting cold, that's a clue, a starting point, and then you have to think it through. Any questions? Yes?
Is it always accurate to determine endo or exo based on where the heat is going, or if it's released or absorbed?
Yes. Yes. Determining exothermic or endothermic, it always has to do with is heat being absorbed or released. The tricky thing is, how do you define what is releasing the energy, what's absorbing the energy? So there's a system and there's surroundings. Because if energy is absorbed, it has to come from somewhere. So the energy must be coming from something. So for that something, it's exothermic, but the thing getting the energy, it's endothermic. Energy is like money in some ways. So if I pay you $5, that's $5 that's gone from me. So that would be exothermic. It left my wallet. But it went into your wallet, so it's endothermic for you. So it's about point of view. When we're asking questions like this, we're talking about the chemical or the matter itself. Water freezing is exothermic. Okay? For the trees in the orchard where the water is freezing, it's an endothermic process because they're getting the heat that's being released. So that kind of makes it a little bit tricky.